density-functional theory. That's an elegant way to approach a tough problem, the many-body problem. Before we think about how to solve it, let us recapitulate the problem. But first, let us realize that this problem is not just an obstacle. When you have a system of many particles in interaction, things can happen that you would have never imagined when you only look at the particles one by one. You can find many-body problems all over, even in movies in the cinema. Look at this scene of the movie Nemo. Nemo discovers how little fish at school learn how to form all together a big fish that might frighten their enemies. Definitely, this is a nice illustration of Anderson's concept of more is different. You can find the reference for Anderson's original article in the lecture notes. An example closer to physics. Look at a drop falling on a water surface. The water molecules behave in a collective way, forming center-symmetric waves. Or look at the two pendula. Each pendulum alone would oscillate in a regular way. The coupled pendula can have a quite chaotic and almost unforeseeable motion. Or think of individual atoms. For example, take two atoms with two different energy levels, like carbon and oxygen. When you bring the atoms together, the two levels interact and might form a bonding and anti-bonding state. The properties of the molecule are very different from the properties of the single atoms. Otherwise, there would be no reason to fear carbon monoxide, since carbon alone and oxygen molecules alone are not frightening at all. So, what is the many-body problem we are interested in here? It is described by a many-body Hamiltonian made of electrons and nuclei. First, we have the kinetic energy of the electrons. The lowercase letters, like I here, label their position. This is a sum of single electron terms. Each electron has its own kinetic energy. The electrons live in the Coulomb potential created by the nuclei. The position of the nuclei is labeled by uppercase letters. This term tells you that the energy of an electron will depend on the position of each nucleus. Still, for the moment, an electron does not care about the other electrons. And then we have the Coulomb interaction between the electrons. Of course, we should not forget to exclude the interaction of an electron with itself. This term forces us to consider more than one electron at a time. Finally, we add the kinetic energy of the nuclei and the nucleus-nucleus interaction. In principle, we should solve this huge coupled problem. The mass of the nuclei is much larger than the mass of the electrons. This means that we can neglect their kinetic energy. And their Coulomb interaction adds just a constant if we consider the position of the nuclei as parameters. So we remain with a Hamiltonian that contains the kinetic energy of the electrons, the Coulomb interaction of the electrons with the nuclei, and the Coulomb interaction between electrons. We can also add some other potential coming from outside, acting on the system. Altogether, let us call external potential the sum of all potentials, including the ones stemming from the nuclei. Why is this still a tough problem? Well, if we write all the arguments of our problem, we see that the many-body Hamiltonian and the wave functions for each state lambda depend on 3 times n space coordinates of the electrons. And there's also the spin sigma of the electrons. You can easily estimate that even for a small number of electrons, the dimension of this problem is exponentially growing. The complication comes from the fact that we cannot separate the coordinates. Can we simplify this? When electrons do not interact, we have n single electron problems. If we also forget the Pauli principle, this means that the many-body wave function is simply a product of n arbitrary one-body wave functions. This looks quite tractable. But wait, it means that all electrons move independently in the external potential. So if I have an external potential and the one electron states, the first electron goes into the lowest state, but so does the second and the third, and we will never get something like a big fish or water waves or any other of the interesting collective effects. Of course, in general, we take into account the Pauli principle, where the many-body wave function is a Slater determinant and electrons with equal spin do not occupy the same state. And of course, we could also optimize the single particle wave functions. But still, the electrons would be independent and the most interesting phenomena would be gone. No, we have to conclude that in general, we cannot make the many-body wave function really simple. Do we then have to live with this complicated beast? Well, the topic of this course is precisely to avoid that. Stay tuned.